Hello, hello! Today we are going to be looking at Chapter 6, Lecture 15, Learning Objectives 5 and 6. So we're going to be looking at our matter waves and uncertainty principle. So in the last video lecture, we talked about the idea of the Bohr model and looking at how that explained the hydrogen spectrum. But there are some limitations to the Bohr model. So first of all, our Bohr model for hydrogen is only for hydrogen, right? So it only describes hydrogen. So it can't describe the spectra of other atoms. And now we're only looking at electrons as particles. We're not looking at them in any other way. So at this point, the only thing that was thought of for the electrons of an atom is that they are particles. And as we know from light, things can act as both a particle and a wave. So since electrons are only viewed as particles, you're losing part of the picture. So we want to look at them in terms of waves as well. It also doesn't fully explain why the electron doesn't spiral in the nucleus. It just says it doesn't radiate energy, therefore it's not going to spiral into the nucleus. It doesn't say anything about the attraction and repulsion and stuff like that. Okay, so there are some important things from our Bohr model. So the importance of the Bohr model. We wouldn't just teach it if there wasn't some important information that we're getting from there. One is that electrons can only exist in discrete energy levels, described by the principal quantum number. So our principal quantum number, remember that is our n value, our integer value, where it can be 1 to infinity. And that energy is involved in the transition of electrons from one energy level to another, and that there's a minimum energy required to have that transition occur. So we're not going to talk about the model, but we're going to talk about a couple more things that are going to lead us to the model that is the current atomic and electronic model for our atom. So come into play, Louis de Broglie. De Broglie? I don't know. He's a French physicist, and he is the first one that was like, oh, okay, if radiant energy acts as both a particle and a wave, so much must matter under appropriate conditions. So our radiant energy, this is our light, right? Okay, he came up with what's called matter waves. So these are going to be waves that matter gives off. Or the wave function of matter. Um, the wavelength of matter is calculated using your wavelength is equal to Planck's constant divided by our mass times by our velocity. Okay? As a note, your velocity being meters per second, your mass needs to be in kilograms because yes, it needs to be in kilograms because Planck's constant is in joules times by seconds. And remember that our joule is also equivalent to 1 kilogram times by meter squared over seconds squared. And then when you calculate this, this will be given in meters, or you'll calculate it out in meters. Okay, now, these are termed matter waves because they describe the wave characteristics of matter. So our matter waves, we're going to describe the wave characteristic of matter. Okay, so if we have a wavelength dependence on mass, which is what we have in the case of matter waves, we would say that mass and wavelength are going to be inversely proportional. They'll have an inverse relationship. So if we want an observable wave, we would have to have a small substance. So if you have something large, it would have an unobservable wavelength. Okay, so let's look at calculating out a wavelength for an electron. So what is a wavelength? Of an electron moving at 83% the speed of light. So this is going to be not light, so it doesn't have to move at the speed of light, but electrons do move pretty fast. Keep in mind that our mass of an electron is 9.11 times 10 to the negative 31 kilograms. So if we want to figure out our wavelength, we're going to use wavelength is equal to Planck's constant over our mass times by our velocity. So our Planck's constant, 6.626 times 10 to the negative 34 joules times by seconds. This will be divided by our mass in kilograms, 9.11 times 10 to the negative 31 kilograms. And that will be multiplied by our speed of light times by 0.83 to give us the 83% of the speed of light. And when we multiply all this out, we are going to get a wavelength equal to 2.92 times 10 to the negative 12 meters. And this also equates to 2.92 picometers. Okay, let's move on. A quick detour into our Heisenberg's uncertainty principle, last thing we're going to talk about in this lecture. So we're going to bring into our discussion Werner Heisenberg. So he was a German physicist. And with this new idea of an electron as a wave, and the idea that waves extend out into space, he was like, okay, if we have a wave that extends out into space, we can't know its precise location. And since an electron behaves in a wave, it is impossible to determine the exact location of an electron. We determined that since an electron behaves as a wave, and waves extend into space, we can't know the precise location of the electron. Okay? So, he said that things that are very, very small, such as subatomic particles, we cannot know both the precise location and momentum of that subatomic particle at the same time for any given instance. So his postulate, so he postulated that the dual nature of matter means that we can't know both the precise location and momentum of an object at any given instance. And of course, like I said, he's talking about subatomic particles. Anything very slow moving like ourselves, we are going to be large enough, we have no uncertainty. So he came up with a kind of statistical way of determining the uncertainty of an electron within an atom. And he said that the change in the location of x is equal to the change in the mass times by the velocity. And this will be greater than or equal to Planck's constant divided by 4 pi. Solving for this using the mass of an electron equal to 9.11 times 10 to the negative 31 kilograms. And what you get is a delta x value that is greater than or equal to 1 times 10 to the negative 9 meters, which does not seem like a very large number until you compare it to the diameter of a hydrogen atom. Which is 1 times 10 to the negative 10 meters. So the diameter of a hydrogen atom is smaller than the uncertainty of where the electron of that hydrogen is. So basically, using this, he determined that there's no way to know where the electron is. You can know its energy, or you can know its location. You cannot know both. Okay, that's everything for this video. We will move on in the next one into our next learning objective number 3. See you guys in the next one. Bye.